Okay, hi guys, we're just going to have a little look at what you've got for this week. So we've been looking back, here's a revision guide. If I open it up, what you've been revising in chemistry is C1 and C2. Okay, we're now moving on to C3 and C4. I'm just going to zoom in a little bit just so you can clear up what those topics are. So C3 is quantitative chemistry. You did this with me before Christmas. Relative formula mass, conservation of mass, concentration of solutions. Remember, we made up different strength cups of coffee, and then we did C4 acids and bases, and we learnt about the different names of acids and what was going on there. And then we went through to reactions of metals, reactivity series, electrolysis. So look, the pages you've got to do in your revision guide, look, it's not very many, is it? 123 to 133. Let's have a quick look then. 123, I'm just going to talk you through the different pages. So we talked about C3, relative formula mass. Okay, here's an example of what this is to do with. It's to do with the mass of these different elements. So let's take one, magnesium chloride. Look on the screen, magnesium chloride, MgCl2. That means we have one magnesium, one Mg, and two chlorines. You look on your periodic table, okay, that will be in your book or on the exam paper or on the wall, and you look up the masses, and you see that the atomic mass of magnesium is 24. It's the number at the top. You have the two symbols, you've got the atomic mass, the atomic number. Chlorine is that, 35.5. So you've got two chlorines, so 2 times 35.5, look at my mouse, and one magnesium, 24. You add them up, the relative mass of relative formula mass of magnesium chloride is 95. You just add up the mass of the individual atoms, elements. Here's a more complicated one. This is calcium hydroxide. You don't need to know that. Ca is calcium, oxygen, hydrogen. Oh, look, it's in brackets twice. So that means you've got one calcium, you've got two oxygens because it's in the bracket, and you've got two hydrogens. So again, you refer to your periodic table if it's not in the question. It tells you the mass of calcium is 40, the mass of oxygen is 16, the mass of hydrogen is 1. So you've got 2 lots of 1, 2 lots of 16 plus 40, and that would add up to 74. And I think hopefully you're okay with doing that. Okay, then we looked at conservation of mass. We did some experiments with conservation of mass. We talked about how if you have the reactants at the start, here's an example, lithium and fluorine makes lithium fluoride look all nice and balanced. If you weigh the mass of these and the mass of that, it should be the same on both sides. The mass is conserved. The mass before the reaction is always the same as the mass after the reaction. Where it sometimes doesn't feel like that, take for instance, you do a simple combustion reaction, you burn a bit of paper, you weigh the paper before, you burn it, and it's gone. And you think, oh, it's lost mass. It hasn't lost mass. It's turned into a gas and it's escaped. You haven't captured that mass. If you captured the carbon dioxide that was made and weighed it, it would weigh the same as the paper did beforehand. So here's a simple question. Show the mass is conserved in this reaction. Lithium plus fluorine makes lithium fluoride. Okay, again, it's balanced. You put in the masses of the individual things. Lithium is 7. So you've got two lots of 7. Fluorine is 19. Look, you've got two 19s there. You add them up, it comes to 52, and then you add the 2 lithiums and 2 fluorines, it comes to 52. It's the same on both sides of the equation. That looks complicated. It's not. You just added up 2 lithiums and 2 fluorines and noticed it's the same number as if you add 2 lithiums and 2 fluorines. If it's anything confusing about that, it's what was the point? It's obviously going to be the same. Okay, so hopefully you got that. Now, you have to be able to explain why in a chemical reaction the mass might appear to go up or down. If one of the reactants is a gas and you haven't weighed it, then that might look like you haven't taken it into account. So again, burning the bit of paper, I weigh the paper, but I haven't weighed the oxygen it burns with. Okay, so that would throw out the mass before and after. If one of the things you make is a gas, the mass could go down. Okay, you've got put some magnesium in some acid, it bubbles, and the hydrogen gas escapes, and you haven't weighed it. So you just need to go through all this and it's all stuff you can do and have done. Then we talked about concentrations of solutions and how the concentration is the mass of the solid thing, the solute in grams, divided by the volume of the liquid, sometimes in centimeters cubed, sometimes in decimeters cubed. A decimeter cubed is 1,000 centimeters cubed. We've just got this simple equation. The concentration is the mass of the dissolved substance divided by the volume of the substance. Okay, here's an example. 30 grams of sodium chloride is dissolved in 0.2 decimeters cubed of water. What is the concentration? It's 30 divided by 0.2, 150 grams per decimeter cubed. It only gets complicated if they give you the volume of solvent in centimeters cubed, and then you have to turn it into decimeters cubed by dividing by 1,000. There's 1,000 centimeters cubed in a decimeter cube. Again, you've got to work through that. I'm just talking you through the pages you need to learn. There you go, boom, C3 done. Okay, let's do C4. Again, being really quick, you're not going to get this at the first pass. I'm just reminding you. Okay, here's a pH scale. Look, neutral. This side's alkali. This side's acid. Here's the colour it goes with universal indicator and some ideas of some different pHs. How do you measure the pH of the solution? You can use indicator, universal indicator. You can use litmus paper, or if it asks you a question how you do it more accurately, use a pH probe like this, and you dip it in and it tells you to a couple of decimal places there. You know, acids and bases neutralize each other. Okay, acid plus base makes salt plus water. Here we are. Let me give you an example. Hydrochloric acid and sodium hydroxide would make sodium chloride and water. We've talked through loads of these in classes. If the acid is hydrochloric acid, the salt is a chloride. If the acid is nitric acid, the salt is a nitrate. If it's sulfuric acid, the salt is a sulfate. Okay, we'll look at some more than a sec. So here we go. You can do every single one of these. Look, hydrochloric acid and copper oxide. What does it make? Copper chloride and water. Sulfuric acid and potassium hydroxide. Potassium sulfate. Look, you see the ending comes from the acid plus water. It's always water. Look, because you've got OH and H. You've got H2O. Two H's and an O. It's water. Okay, nitric acid and sodium hydroxide. Guess what? Sodium nitrate. You see the pattern? Plus water. Where does the water come from? Oh, look. OH and H. H2O. Water. And that's why it's neutral. That's why acid plus alkali makes neutral. It's why it's a neutralization reaction, because the acid, things are acid because of the H, things are alkali because of the OH, and we've neutralized them, we've taken them out. Okay, another little experiment we did. If you put an acid with a carbonate, it makes the salt, look, sodium chloride plus the water. We've got our H2Os in there, but it also makes carbon dioxide gas. Remember, we collected carbon dioxide gas. Test for carbon dioxide, it makes lime water go cloudy. Okay, and then this was our required practical where we made a salt. So we took some copper oxide and hydrochloric acid. We poured the copper oxide into the hydrochloric acid. It makes copper chloride and water. Good. Copper, chloride, and H and O, water. Look. Okay. We filtered out the excess copper oxide. It's a black powder. Excess means there's too much of it. Okay. And then we warmed the copper chloride to evaporate the water, and it left us with copper chloride crystals. And that was our required practical. Okay, and we looked at the reactivity series, which metals are more reactive than other metals. Here we are. And then importantly, we've got carbon and hydrogen in there. It's important to know where they fit in, because that's to do with extracting metals. Okay, so if the metal is less reactive than carbon, like iron for instance, when we've got iron oxide, iron ore that we dig out of the ground, we want to get the iron on its own. All we do is we burn it with carbon. The carbon takes the oxide bit away from the iron, leaving just iron. Okay, that's a very cheap way of extracting the metal from its ore. If it doesn't work with these ones that's above carbon though, we have to use electrolysis, which is a more expensive way. Okay, so you've got, we talked about oxygen. Gain of oxygen, oxidation is gain of oxygen, reduction is loss of oxygen, and we talked about how you could extract metals by reduction with carbon. Again, you're going to have to read through it. We've done it, but you're going to have to read through it. Okay, different reactions of metals. Here we talked about acid plus metal makes salt plus hydrogen. You've just got to look at the things here. Look, hydrochloric acid and magnesium. Magnesium chloride. Why is it hydrogen? Because there's no O's in this. Let's look at the formula. Magnesium chloride. What have I got left behind? Two H's. Okay, because it's the magnesium on its own. It's not magnesium oxide. I don't make water. There's no H2O. It's just H2. What's the test for hydrogen? It's a squeaky top pop test. I put a lit flame in. Metals reacting with water. Metal plus water makes metal hydroxide plus hydrogen. Here's an example. That's a harder one to remember, isn't it? You just got that. And there we are. And then the last little bit, was electrolysis. Electrolysis means splitting up with electricity. Elec means electricity. Olysis means splitting. And we looked at how electrolysis only works if the thing you're splitting is either dissolved or melted, because the particles have to be free to move. Okay, and here is a complicated looking diagram, but this shows us doing electrolysis with this stuff, aluminium oxide, like aluminium and oxygen. What happens? Here's our melted, molten means melted aluminium oxide. This is our cathode, the negative electrode. This is our anode. Aluminium makes a positive ion, oxygen a negative ion. Why is that? Oxygen's in group 6 of the periodic table. It's got 6 electrons in its outside shell. When it gains 2 electrons, it gains 2 negatives to have a full outside shell, 8 electrons, go from 6 to 8. It's got a 2 minus charge, it's gained 2 negative electrons. Aluminium's lost 3 negative electrons to make it positive. That doesn't matter with this, but just for thinking that the oxygen goes to the positive electrode, the anode, because opposites attract. Aluminium goes to the cathode, look, opposites attract. The positive's gone to the negative, so we split the aluminium and the oxygen. It has to be melted because the aluminium and oxygen particles need to be free to move. Ions need to be free to move. And that is more or less it. You've got another couple of examples of electrolysis that you need to learn, but it's the same idea. That you've got your charged particles. This is copper sulfate. Look, copper is positive, goes to the cathode, and then you've got sodium chloride. You've got chlorine goes one way, and you've got, the hydrogen from the water, the H2O, goes the other way. This gets a bit complicated, and you're just going to need to spend some time reading through it, and I'll go through it when we're back in lessons. I'll remind you of it, because that electrolysis, when students are talking about stuff they don't get, electrolysis is always on the list. So I'll go through this with you a bit more face to face, but read through it, and then that is the whole topic. That's all your revision done. Okay, so please take your time. Okay, everything I've been through, all that there is, I don't know, term and a half's stuff that we'd have done in class, C3 and C4. In 10 minutes for me to go through that, and you hopefully to be thinking, oh yeah, I kind of know that bit, I kind of know that bit, means it's not that much. And if you sit at home for a couple of hours, just go, well, not 2 hours in one go, but just go through it, spend a couple of hours, spend 15 minutes a page reading through, making your notes, working through the questions. You'll be in a really good place. The only thing there that I think most of you will struggle with, because everyone does, is the electrolysis at the end, but don't worry, I can go through that with you when we're face to face. This other stuff you can, because we've taught it before, you will be able to figure it out. Just take the time and go through it.